So today, the title of my talk is Adventures with Systrace. Subtitle is Measure and Investigate the Glass-to-Glass Latency in Android. Just to get the expectations clear, it's not an introduction to Systrace. It's more a marketing show, a marketing talk for Systrace. So I explain how cool stuff I found out about cameras and displays and the Android graphics subsystem with Systrace and other stuff. So yeah, it's not an introduction. It's just cool technical stuff with Systrace. So some words about me. I'm Steven Lenkfeld. I'm an Android and Linux system developer. I work for 6 years at Innovex. I have 8 and more years experience as a professional embedded developer and many more years experience as a programmer and a general Linux enthusiast. So let's go into the topic. What I'm talking about is today is the glass-to-glass latency. What is the glass-to-glass latency? It's a property of a system which has a camera and a display. For example, a camcorder, or for example, an Android phone which has a camera and a display. And you see, for example, you have the camera, and the camera points to an object like a face. The face emits photons. The photons are captured by the camera, by the sensor of the camera. They're converted to electrical signals. These signals are transferred to the SoC, to the RAM. Then some magic software code runs, pushes some jobs to the GPU, renders some stuff, generates a final screen image, and then the screen image is again pushed out to the display where it's displayed, and then the display emits photons, and these photons are received by the human eye. And the glass-to-glass latency is the time between the photons hitting the first glass, the camera, and the photons hitting the last glass, the display glass. Okay, this is the property we want to measure about our setup today. Why is the glass-to-glass latency important? So for us, it was important not at all, but for one of our customers, was it important? The customer came and asked, hey, what is the minimal glass-to-glass latency in Android? And we had no idea. So yeah, we started our investigation, which this presentation is about. So why you need it? You need it for augmented reality, virtual reality, and mixed reality. In these cases, for example, you have not expressly a phone before you had, but some kind of phone, HoloLens or Google Lens, or these stuff for virtual reality headsets, which have a display in your sight, which is either semi-transparent or non-transparent. In the semi-transparent case, you still receive the light from the outside world. In the non-transparent case, you do not receive the light from the outside world. But these systems sometimes have cameras which can record the outside world and then project into the inside world. And the latency is important when you move your head, because the outside world or markers which are presented in your sight should stay at the same position. And so you want to reduce the latency between tracking objects and showing them on the screen. So you don't see a lag and it should feel totally normal. So that's why the glass-to-glass latency is important and a nice, important property of some systems to optimize for. My test device was not a Pixel 5, it was a Pixel 2. It's a very old phone. It was first released in 2007 and discontinued in 2019. And here you see an image on the Pixel 2. Why I've chosen on this device? Because I had it on my desk. That's the only reason. And another reason is that I could build a vanilla AOSP for it and became root on the device, because all my investigation at the end needed root on the device. The device seems outdated, but in fact, the properties I explained today are still the same for newer devices. I have done the same measurements with my current smartphone and also with an iPad, and you get mostly the same results. So the technology behind it is still the same. And one important aspect for my tests here, the display of this device is running at 60 Hertz. So 2 frames are 16 milliseconds apart. This number will come up often now. And the camera is running at 30 Hertz. So we have between 2 frames, 33 milliseconds. So how to measure the glass latency or not? If you search on the internet for the topics, the first test or measurement setup that comes up is this example. So take a stopwatch, which shows the time in milliseconds. Then take your test device, here the Pixel 2 phone in the front, and point it to the stopwatch, and then take a picture of, and then use the camera web of the device to make a video and then take a picture of the whole setting. So now you have two numbers, the stopwatch from behind and the image of the stopwatch. You subtract the numbers, and then you have a rough idea or how the things or the people on the internet say that's the glass-to-glass latency. And here in my case, we have 83 milliseconds. So first impression, okay, we have a number, but is this number correct? What is going on technically? Because what you can all see already is that this number on these displays are smearing into each other. So it's not a precise measurement we're doing here. There are some error bars. So I want to find out the error bars, but to take the attention now this number is correct. 33 milliseconds is one of the correct glass-to-glass latencies for this setup, but the more precise answer is 57 to 106 milliseconds. And so it's a range, and why is it a range, and what is happening technically? That is this presentation about. What I have done to find this out, I have built my own test setup, which is a more sophisticated than a stopwatch. So I used LEDs, I used photodiodes that are like LEDs but can receive light, cables, resistors. I used coffee mugs and a lot of coffee, and a power supply to power my electronics. I used an oscilloscope, which is not running Android, it's running Linux, and an Arduino, and of course Android systrace, because Android systrace is cool. What is Android systrace? It's the Android system tracer. It's built upon the Linux ftrace framework, so you get all the nice trace capabilities that the Linux kernel has for free. So you know about processes, you know about schedule events, you know about IRQs, you know about driver subsystem events like I2C messages. But systrace also includes a lot of trace events from the Android user space. For example, trace events from the software slinger, events from the GPU, events from the hull, events from binder, events from the camera server. And you can also use Android systrace in your own project, in your own applications. In Java and Kotlin, the methods are called trace begin section and trace end section, and in C++ and C, a trace begin and a trace end section, which you can just put in your code, and then you have these traces in the trace log. And the nice thing is about the Android system traces that all the traces from all the layers are combined in one single trace file, which you can look at. So how to use it? Systrace is it's a Python script in the Android SDK, which you can start. It has a bunch of config options. I have a lot of config options here, but most are not important, which you can leave out in your first twice, and you can set a time, an output file, and also an application name, but for the first time you don't need it. After you trace your system for 2 seconds in this case, you can open this trace file in your browser, and then this systrace GUI is the opening, which I show in 1 second. Where you can look then and this systrace and it takes the introspection. But one note here, there's a project called Perfetto. It's actually quite old. It's another, as far as I know, is another GUI for systrace files. So you can put your systrace files into that GUI, and it's I think a better GUI for it. I have not tested it yet, but it's kind of the next gen systrace thing. I don't know. Please check it out. I still use the old systrace GUIs. How the systrace GUI is looking. So here, this is a screenshot. On the left side, you see your applications or processes. Here, you see my latency test application. It has a bunch of rows. Some of these rows are threads. For example, you have the UI thread. You see what the UI thread is doing. You have the render thread. You see 3 binder threads. But you see also other events Android is attaching to the systrace. For example, GPU completion, which is about when your app schedules jobs on the GPU to render something, then you see if your app is currently doing something with the GPU. And in the main screen, the time is flowing from the left to right, and every trace event is showing up as a colorful box, which you can see here, which you can click on it, and you see the name and the duration and the walk clock time, and also these trace events can nest. So you can also have these kind of towers where you can look into it. And the very nice thing is that you see the scroll bar here. So it's really huge. So you see all processors and you see the CPU cores on your system, and you can then correlate something that happens in your app to something that happens in Software Slinger and something that happens at the kernel. That's very nice about this trace. So with that, and 4 weeks of work, not full time, but 4 weeks of work, 15 tests about setup and technical stuff, a bit of cabling, hardware cabling, and looking at a lot of system traces, I got this setup. So this is an electrical drawing of my setup, and on the right side, it's an image of it. So on this side, I have an LED, which is shining directly into the camera. It's connected to a button and a resistor. So when I press a button, the light shines up and shines directly into the camera. So I can control when the camera sees black or white. And the button is actually connected so I can control the program programmatically, not via my button press. So, but now this light is received by the camera. Then these have the Android smartphone in the middle, which does the processing of the image. And then we have on the other side the display. And on the display, I have placed a photodiode. This photodiode will change its resistance when it will receive dark or no light or a lot of light. So when the screen shows dark or white, the voltage will change, and this voltage change I can measure and also show on the oscilloscope. So on the oscilloscope, I will have 2 traces, one of the LED blinking up and down or going up and going on and off. And on the other side, I will have a voltage line watch the display. So if it's displayed black or white. And now, after 4 weeks, I got this. On the top, you see a sys trace graph, and on the bottom, you see a capture of the oscilloscope. And here at the top one, I've annotated what is happening at which instant. We will go into that in a moment. So below here, you see the blue voltage line. It's the LED and markers that I used. And here you see at this point, the LED is going white for 33 milliseconds, then it's going down. And sometimes later, the yellow line, which is the photodiode connected to the display, the photodiode is going up. And at this time, my white image I produced at the camera is actually showing up on the display. And with that, I can exactly measure the time between an input event or the image or from the camera and the output event on the display. And already so get a closer look. So now I have the outside world, the voltages correlated to the inside world. This is trace graph. And what we see here is that there's a time 31 milliseconds, 33 milliseconds from the camera sensor, then 22 milliseconds time between the camera sensor has received the image and the image available callback in the app fires. That's the time when the app gets the full frame from the image. The app will then render the image on the display. This is happening here. And this will, when it's rendered and pushed to the Android surface, to the Android display stack, Surface Slinger and co, it will still take 33 milliseconds until the pixels on the display go up. One important point I want to mention here is that you see here white and gray parts on the sys graph, and this is exactly 60 milliseconds, and that's the time you roughly refresh rate of the display. So already Android sys traces correlate nicely events to things that happen on the display. Okay, now we have the components of the glass-to-glass latency. We have 1 to 33 milliseconds camera exposure. I will explain a bit more later. 24 milliseconds sensor to app, from the sensor image to the app, so we can do something with the image. Then we have 33 milliseconds processing in the GPU, Software Slinger, and vSyncs, waiting for vSyncs. more about later, and 0 to 60 milliseconds scan out time on the display. So with this, we have a better understanding of the glass-to-glass latency. Now the glass-to-glass latency is a range from 57 to 106 milliseconds. But we don't know not why. So here are the details. First, we look at the camera sensor. We talk about rolling shutter and skew time. Then we look to the display scan out, and then we look at rendering and resyncs. What is the rolling shutter effect? So the sensor does not exposure all pixels at the same time. The exposure starts row after row. The sensor is a grid of pixels, a lot of pixels, 20 megapixels or 40 megapixels. And not all pixels are exposed at the same time, but they're exposed row by row. It starts at the top, at the first row, and then the second row is exposed, and then the third row, fourth, until the last row of the sensor is exposure. And because there's a time delta between these exposures, a thing that is moving very fast on an image is kind of not the same in reality. For example, at the upper left, you see a photo that I've taken from a cockpit of an airplane with a rotating propeller, and the propeller is rotating really, really fast, and the propeller is actually straight. But because we have the time deltas between the actual exposures of the row, the propeller shines banded in the image. That's the rolling shutter effect. It's kind of a motion blur that we know from digital or analog cameras when something is moving really fast, but it's different because these normal analog cameras have not a rolling shutter, but they have a straight shutter, so they does not have the rolling shutter effect, they have only motion blur. Android cameras have the rolling shutter effect and motion blur. And the time between the first exposure of the first row and the exposure of the last row is called the skew time. And how long is the skew time? I have done some tests with an Arduino in the upper right. Here I have programmed the Arduino to make the LED on and off really, really fast, except especially 2 milliseconds apart, and then capture an image of that. And with this test, I have tried to figure out whether the exposure time, so how long the rows are exposed, that affects the skew time, so the time between the first row and the last row. And the answer is it does not affect the skew time. So which exposure time you choose, short or long, the skew time is always 32 or 33 milliseconds apart. So the first row and last row are really 32 or 31 milliseconds apart. It cannot go faster, at least not in my system without tuning. Now we have talked about the camera sensor, now talk about this display scan out. This is my test I set up for the display scan out. So what happens at the display? So I have placed a photodiode at the top of the display and a photodiode on the bottom of the display. And I've programmed an app that switches the pixels of the display to white for one frame and switches back to black for all other frames. And if you take this and measure it on the oscilloscope, you see the following image. So the yellow graph is the photodiode on the left, and the blue graph is the photodiode on the right. And you see there's a difference between the pixels lighting up. So a display is also not refreshed at once, so all pixels are not refreshed at once, but there's a time between the pixels. And in this measurement, exactly the time between the upper part and the lower part is 12 milliseconds. 12 milliseconds, that is nearly exactly 60 milliseconds. This is the refresh time of the display. So these pixels are refreshed pixel by pixel from left to right and then from top to bottom. And this whole process takes nearly the whole frame time until the next frame starts. So I have to drink something. Okay. So my voice is collapsing a bit. So rendering and resyncs. We try to continue. There are 3 resyncs in our Android system. One is the hardware resync, which is the real resync. So the resync is that point when the hardware starts scanning out the first pixel at the top left pixel on the display. This is the hardware resync. Then we have a second resync, that is the surface play Singer resync. That is an event which also happens every 60 milliseconds when surface flinger is composition a new frame. So it takes the image from the app, it takes the status bar, and it takes these buttons and then composites that together to a whole screen, and then this screen is given to the display. And there's a third resync, that is the app resync. That is an event that also happens every 60 milliseconds. That is when the apps get an event and starts reading input events from the touch screen and mouse, and starts rendering his own screen and then giving that to the surface flinger. This setup is called triple buffering because there at one point in time there are roughly 3 buffers active at once, one for scan out, one for surface flinger, and one for the app. Again, a sys-trace graph. I want to show that because here you see the sys-trace of surface flinger, and surface flinger has also a row which is showing when the resync app is happening. This is this line, resync app, and one row that is showing resync surface flinger. This is when the surface flinger event is coming in and surface flinger starts composition. And here below you see my app, which got the resync app event. Here you see traces for me, and here you see a trace that is called EGL. It's the function is called EGL swap buffers. This is the time when my app has finished rendering and submitting the job to the GPU, which is then rendered by the GPU. And here you see also the GPU work is doing so for a very short amount of time. The GPU is rendering the screen, and then it's giving to surface flinger. So that are the details. Let's go back to the first graphics. So I have explained why the sensor exposure really takes 33 milliseconds, and it does not depend on the exposure time. Sorry again. Then I've shown you that it takes time from the camera sensor that the image is returned to the app. Then there's the time because of triple buffering that the app renders the image until the until the screen is scanned out to the display, and the actual scan out to the display also takes time. It's 60 milliseconds. So again, the latency is a range. So recap. Nothing has happened instantly. Exposure of different pixels happen at different times. Updating pixels of displays happen at different times. So the glass-to-glass latency is a range. Second, it depends on which pixels you light up and measure. So first row for the last row of the sensor, and the first pixel and the last pixel of the display. This was the technical stuff about my talk. As I told you, it was not an introduction talk. It was a marketing show for sys-trace. Oh, you cool things you can find out with sys-trace. So yes, I love sys-trace. Every device I get and have a performance issue, I just open up sys-trace and try to figure out what's going on. And because sys-trace is a tool to inspect and debug your performance issue on Android. Further reading. So glass-to-glass latency is important for virtual reality. So there are some blog posts about it, which these blog posts contain also the topic about the glass-to-glass latency I talked here, but it's only a short part of it, because these topics talk more about the challenges, because this latency can hardly be reduced. But if you have a virtual reality headset and augmented reality, this latency is too short, but that is too long. You want shorter latency, and how they work around this is presented in this blog post. So yeah, read them up and find it out. I have also some code to share, some tests I did, the application I wrote, some things I've done, I have posted on GitHub, see a link. And the slides are also shared by Quest. So you don't have to, you get the slides and the links. Thanks. Time for questions, and sorry for my voice.